Hey there. Welcome to Concise MD, your go-to for crisp, clear, and quick medical videos. Today's topic is cell injury. The most common cause of cell injury is hypoxia, a lack of oxygen at the cellular level. The most common cause of hypoxia? Ischemia, where blood supply gets cut off. Neurons are the most sensitive. Give them just 3 to 5 minutes without oxygen, and they start dying. Meanwhile, fibroblasts, completely unbothered, oxygen or not, they just keep going, like the overachievers of the cellular world. The two types of cell injuries are reversible cell injury and irreversible cell injury. So what really happens to a cell when oxygen drops? Let's break it down. First, less oxygen means the mitochondria can't function properly, and that means less ATP. No ATP? Well, the sodium-potassium pump fails. And when that pump fails, sodium starts collecting inside the cell. And where sodium goes, water follows. So now the cell swells up. We call that hydropic change. If this continues, the cell gets bloated like a water balloon and may even start forming myelin figures, which are just bits of the cell membrane curling up like leftover trash. But wait, there's more. The lack of oxygen also pushes the cell into anaerobic glycolysis. That means the cell tries to make energy without oxygen, but ends up making lactic acid instead. And lactic acid, it drops the pH, making the environment acidic. This acidic pH messes with the nucleus, causing the chromatin to clump. The cell isn't dead yet, but it's definitely in survival mode. Good news? If oxygen comes back in time, the cell can recover. That's why we call it reversible injury. The rough endoplasmic reticulum, or RER, makes proteins. It's called rough because it's covered in ribosomes. But when the cell is injured, those ribosomes detach. And without ribosomes, protein synthesis drops. Simple as that. Let's look at the key changes in irreversible cell injury and how they differ from reversible damage. In reversible injury, the damage is mild. The Na plus K plus ATPase pump slows down. Cells swell and metabolism shifts. But if oxygen returns, the cell can still recover. In irreversible injury, the damage crosses a critical threshold. Step 1. Na plus K plus ATPase pump failure. ATP is completely depleted. The pump shuts down. Sodium rushes in. Water follows. The cell swells massively and bursts, forming myelin figures, degraded membrane remnants. Step 2. Anaerobic glycolysis. With no oxygen, the cell switches to anaerobic metabolism. This increases lactic acid, drops the pH, and causes nuclear chromatin to clump, a sign the nucleus is on its way out. The big difference. Reversible injury is like fainting. You can bounce back. Irreversible injury is like falling into a coma. There's no turning back. The membranes are gone. Irreversible cell injury, ribosomes detach from the rough endoplasmic reticulum. And that's a big deal, because ribosomes are responsible for protein synthesis. Once they're gone, the cell can't make essential proteins anymore. That loss is critical, and unlike in reversible injury, this damage can't be undone. Two defining point of no return moments in irreversible cell injury are 1. Mitochondrial damage, meaning no more ATP, no energy, and cell death is inevitable. 2. Membrane damage. Both plasma and lysosomal membranes break down. leading to enzyme leakage, calcium overload, and self-digestion of the cell. At this stage, recovery is no longer possible. Membrane damage allows calcium to enter the cell and deposit on mitochondria, forming amorphous flocculent densities. These fluffy calcium deposits signal mitochondrial damage, which means the injury is now irreversible. Remember, amorphous flocculent densities equals mitochondrial damage equals irreversible cell injury. It's a key exam point and a point of no return for the cell. In irreversible cell injury, the nucleus undergoes 3 key changes. Diagnosis: the nucleus shrinks and chromatin becomes dark and dense. 2. Karyorrhexis: the nucleus breaks apart into fragments. 3. Karyolysis: the nuclear material dissolves, fades, and disappears. Point. Final step: the nucleus is gone, confirming cell death. These changes are classic markers of irreversible injury in pathology. Let's quickly revise cell injury. When stress exceeds a cell's capacity to adapt, injury begins. Reversible injury: the cell can recover if the stress is removed. Key signs include cell swelling, fatty change, membrane blebbing, myelin figures, ribosome detachment, decrease protein synthesis. Irreversible injury: point of no return, leads to cell death. Key features: membrane damage, mitochondrial damage with amorphous flocculent densities. Nuclear changes: pycnosis, karyorrhexis, karyolysis. Tip: reversible is fixable. Irreversible means the cell is gone.